Today we're going to talk about various notions of connectivity in graphs, and we're going to come up with several concepts that are different, yet in some ways very related to each other. So we're going to start with the oldest problem, and that is the problem of the bridges of Koenigsberg. This problem was posed and solved by Euler in 1736 and is considered one of the first problems in graph theory because he actually solved it in the language that we still use today in graph theory. The problem is as follows. He was actually walking around a city, Koenigsberg, and this is a picture of the 7 bridges that were located in the town center across the river. What he was wondering is it possible to start somewhere in the city, anywhere really, go for a walk, and cross every bridge exactly once, and also come back to the origin where you started from? This is a really fun puzzle, so I encourage you to pause the video, take a minute here, and try to see if you can start somewhere, anywhere. It really doesn't matter. Pick your favorite starting spot where you would like your house to be. For example, maybe you'd like your house to be on an island. And then try to go around for a walk along the bridges with the goal of crossing every bridge exactly once. So this walk of mine failed, but maybe yours will succeed. Now, the way that we can conceptualize this in graph theory is by introducing what would be our vertices, what would be our edges, and how we will introduce those edges. So what I'm going to do is I'm going to label the disconnected by bridges pieces of land with names. So I notice that this is one piece of land that has 3 bridges attached to it. So this piece of land I'm going to call piece A. I notice that, for example, my island is disconnected from the rest of the land. I'm going to call it B. This bottom part I'm going to call C, and this part I'm going to call D. And now what I have for myself are these as vertices of the graph. So I'm going to write them on the graph sort of in the same way, in the same geographical location. Although remember, in graphs, it really doesn't matter where I locate the vertices. I'm going to keep them at least similar to the picture. And I'm going to connect 2 vertices if there is a bridge connecting those separate pieces of land. So for example, my bridge 1 goes between A and B. So I'm going to introduce the edge between A and B. But I also notice that bridge 2 connects A and B. So I'm going to connect A and B with another edge again. So in this manner, what I actually have is, in fact, a multigraph, not a simple graph anymore as what we've been talking about, but it's simple enough because there's only 4 vertices. And continuing in this manner, I can see that B and C are connected by 2 different bridges, labeled 5 and 6 in my picture here. B is connected to D by a bridge, C is connected to D by a bridge, and A is connected to D by a bridge. And so my picture here actually corresponds to this graph. Now, it might be a little bit easier trying to now think about the problem without getting sort of lost in the geography of the situation. So the question becomes, can you walk along this graph starting somewhere? So pick your favorite starting spot. Can you walk along this graph so that I am back to this exact same point and I have walked along every single edge? Because remember, edges correspond to bridges. Again, maybe take a minute and try to see if you can now do it on the graph. Or maybe you notice that something breaks down that is now obviously broken on the graph that wasn't obviously broken when you were looking at the more geographical picture. So depending on how stubborn you are, you might have spent a few seconds to a few minutes on this, you will notice that it is not possible to do that. And that is basically what Euler proved in 1736. And in his honor, the circuits that he was trying to find in this graph are called Eulerian. So an Eulerian circuit is a circuit that contains every vertex and uses every edge. Now, generally, we actually say that it's a circuit that uses every edge because by the virtue of using every single edge, it has to, of course, use every single vertex because edges are nothing but connections between two vertices. Now we have to say every edge in the case of multigraphs. So for example, here I will have to use both of these graphs or both of these edges and not just one of them, right? So it is important to notice that you do have to specify to use every single edge. Now, before we try to think of what conditions might be necessary and sufficient for having an Eulerian circuit, let's explore a few other small examples. So here we have graphs of all different types. Do these have Eulerian circuits? Well, this first one I can clearly see does, because it doesn't matter where I start. Let's say I start here. I mean, it's a circuit, so it really doesn't matter where I start. I can simply walk around in a cycle, come back, and I have visited every single edge. So yes, indeed, this graph has an Eulerian circuit, and therefore we actually call it an Eulerian graph. Now here, the graph is exactly the same, but I've introduced one more edge. And remember that I have to use every single edge. So by introducing this, I now have to also cross this edge over. And the same for all of these other graphs. I'm going to have to go through every single edge and come back to the vertex that I started with. So take a minute here, pause the video, and try to figure out if you can construct such circuits in these graphs. It shouldn't take you long to persuade yourself that in this graph, you are not going to be able to cross every single edge. This one is possible, so this one is Eulerian. This one is not possible once again, and the path is very clearly not Eulerian simply because if I start anywhere, I won't be able to come back, for example, to this vertex, right? I can follow the graph along, but Eulerian means I'm able to close the circuit, and the path, it doesn't have a cycle at all. So this is clearly not Eulerian. Now, if you've gone through the actual examples and paused the videos like I asked you to here, you have probably already discovered some intuition behind when it's clearly not possible. So for example, for this graph here, the cycle was completely perfectly possible and Eulerian. The introduction of this edge, though, ruined the property. And the problem here is, notice that, for example, this vertex. I have to come into this vertex and I have to come out of this vertex, which leaves me with this edge that I have to use to make an Eulerian circuit. But if I enter the vertex along this edge, I have no way out. So vertices of odd degrees are a problem. And this is essentially the defining rule for a graph to have an Eulerian circuit. In fact, this rule is so strong that it forms both necessary and sufficient condition for the graph to be Eulerian. So we here have the following theorem. A connected graph, it has to be connected. If it has two different pieces, maybe pieces are going to be Eulerian, but the whole thing is not going to be Eulerian. So a connected graph is Eulerian. And again, that means it has an Eulerian circuit. If and only if, so necessary and sufficient, every vertex has an even degree. So you can notice from above that this rule seems to hold. If everything has an even degree, then we're guaranteed an Eulerian circuit. The moment we introduce vertices of odd degrees, the property seems to break. The surprising part here is that it's necessary and sufficient condition. So I'm able to figure out, given a graph, by just looking at it and checking the fact that all vertices have even degrees, that it is Eulerian. Constructing a circuit is a bit of a different story. But we're at least going to be able to guarantee that it is Eulerian, and you just have to persevere in order to find the circuit. Let's prove this result. The proof is really quite intuitive in this case. So we're going to have to prove both directions, the necessity and the sufficiency. So first, let's prove the forward direction. So I'm going to suppose that the graph is Eulerian, and I'm going to justify that every vertex needs to have an even degree. So I'm going to suppose that my graph G, let's call it G, why not give it a name, is Eulerian. Now, if it's Eulerian, it means it has an Euler circuit. So let's say my Euler circuit is going to be V0, V1, all the way to some Vk and back to V0. And this is my Eulerian circuit. Let's draw a picture here because a picture is always just a little bit more intuitive in these types of arguments. Okay, so I'm going to go all the way down to some vertex Vk and connect it back down to V0. So this here is my Eulerian circuit. Now, the justification here is really along the same lines as we would have discovered by doing the exercises. Every time my Eulerian circuit passes through any vertex along it, it contributes 2 to the degree of that vertex. I have to be able to come in along the edge and come out along an edge, which means that I have to have 2 edges for every single vertex. Now, this circuit might actually go back through the same vertex more than once, but every time I go in, I have to come out. So every time I contribute 2 to the degree. And any multiple of 2 is, of course, an even number. Therefore, every single degree of the vertex is going to be even. Won't necessarily be 2, might be 4, but it will be even. Now let's prove this theorem in the opposite direction. So that means I'm going to assume that every vertex has an even degree, and I'm going to show that it implies that the graph needs to have an Euler's circuit. So my assumption is that every vertex has an even degree, and my eventual goal is to prove that the graph is Eulerian. Now, this is going to be a constructive proof. So not only are we going to actually prove that it has such a circuit, we will actually construct it. We will construct Eulerian circuit. So how are we going to begin? Well, let's start with some vertex. I'm going to pick a vertex to start with. Any arbitrary vertex will do. Some vertex, let's call it V0. And what I'm going to do is construct a circuit through it. Any circuit. Construct Okay, so I have my vertex, let's call it V0, and I have managed to construct a circuit. Sort of. I haven't actually justified why I am able to yet, so let's talk about that. How can I guarantee that I can construct such a circuit? So let's call it, for example, V0, V1, all the way up to Vk and back to V0. What guarantees do I have that that's even possible? Well, my only assumption is that every vertex has an even degree. So that means that for any single vertex in the graph, in my graph G, some random graph G, every vertex has an even degree, so has an edge going into it, and it has an edge going out, which means that I can certainly construct some kind of circuit. Okay, so notice here that this is possible only because I will have for every vertex an in edge and an out edge. And this, in fact, immediately, for example, disqualifies trees from being possible to construct an Euler circuit with. So, for example, something like this. If it doesn't have a cycle at all, it has leaves, vertices of degree 1, which this prevents from having, it will not have an Eulerian circuit. Okay? But because here everything has an even degree, for every vertex, I'll be able to get in and I will be able to get out, so I can construct some kind of a circuit. Now, if this circuit already visits every single edge of the graph, then I'm done. It's Eulerian. So let's call this circuit C. And my next justification here is if C is Eulerian, then we're done. Now, what if it's not? If it's not, what we're going to do is we're going to basically take it out of the graph and think of the graph as the remaining of the edges and the vertices. The graph we started with is connected. which means that if I simply take out this circuit, there will be some edges that connect it to the other graph. There will be some vertices in common with that. So for example, let's say that this vertex right here, let's call it VS, some special vertex VS, will be connected to the rest of the graph G. And then I can repeat this exact same process starting with the vertex VS as opposed to V0. If I repeat this process here, I will be able to, once again, because the degree of every vertex is even, if I took out this circuit, I took out the degree 2 from every vertex involved, which left me with still even degrees for everything. And I'll be able to then find a circuit for this special vertex VS. Now, I can combine my original circuit and this circuit in one mega circuit. If this circuit is Eulerian, then I'm done. And if not, I'm going to repeat this process again. Notice that because I start with the connected graph, and of course it is on finite number of vertices, that means that this process is finite. And in the end, one of these circuits, in however many iterations it takes me to get me there, will in fact be Eulerian. Okay, so I'm not going to write out full wording of the proof here. I just wanted you to see how one might justify the existence of an Eulerian circuit from a very simple assumption of evenness of every single degree. So I'm going to just say repeat, and I'm going to say glue circuits together until they cover all edges of the graph G. Okay, so you can see how you can use this constructive method to actually apply to find Eulerian circuits in the graphs where every vertex is of even degree. So for example, let's apply that algorithm to this graph here to find an Eulerian circuit. You can pick your favorite vertex to start with. So let's say I'm going to start with this one, call it V0, and I'm going to construct a circuit on it. It doesn't have to be Eulerian right away, it just has to be a circuit. So I'm going to do it one way, you can potentially do it in a different way, of course. So let's say my first circuit is going to be this one. Now, is it Eulerian? No, it's not, because it doesn't include a whole bunch of these internal edges of this construction. So I know I'm not done yet. So now I have to disregard all of the edges that I've already used and pick a new vertex to start with. So let's say I pick this vertex, VS, to start with, right? And then starting with this one, I have to now construct a circuit on so far unused edges. Okay, so following the edges along, let me make it next one pink, I can see that my circuit can be this one. And now, between my two circuits, I've actually covered the entire graph. All I have left to do is to think about how to combine them both. And here, I think that looking at the general picture helps. I started with V0. I have to go all the way to my special vertex, cover the new circuit I've created, and then come back around to V0. So that's what I'm going to do here. I'm starting at V0. I'm following my blue circuit, the first one I constructed, and until I hit that second vertex that I chose. And then I'm going to switch to the pink circuit, come back to VS, and then cover the rest of the blue circuit as I was going along, therefore constructing the Eulerian circuit for the entire graph. Isn't this lovely? So Euler asked, can you traverse a graph so that you go through every single edge? The next natural question to ask is, can you traverse a graph so that you go through every single vertex? And that question was asked in 1857, so quite a bit later, by an Irish mathematician, Rowan Hamilton, who invented the so-called around the world puzzle. He actually worked specifically on a particular graph that was a regular dodecahedron, which is a three-dimensional figure. So you can think of that as sort of a soccer ball type structure where these dashed edges are on the other side of the ball. And in order for us to come up with a more representative picture of the graph, basically think about squishing this face of it into the back one. So punch your soccer ball onto this side of it, squish the whole thing, and you're going to get this graph. So you have, like, for example, this 5 cycle is your outer face here. So everything has been squished into it, and all the other vertices appear in the middle. So the puzzle was that every vertex represents a major city in the world, and every edge is a route between two cities. So you're no longer interested in going along every single road. What you are interested is finding a route that goes through every city exactly once. Those things are now called Hamiltonian circuits, a cycle that contains every vertex in, of course, with Hamilton as their inventor. So here's the same graph. Both of these represent the same graph. Maybe pause a minute and see if you can find such a cycle in this graph. You can start at any vertex because, once again, you're going to want to go through an actual cycle. So let's say I decide to start at this top one here. Then what I can do, it's not that every circuit is going to be unique. Here's just one of them. So I can go down, and then I can traverse a little bit of my internal structure here in this way. And then at some point, I better make it all the way out into the outer cycle to make sure that I touch the vertices there. And there is my Hamiltonian circuit. Now, the next question is, if you have other graphs. So the original puzzle has a solution as opposed to the Euler's original puzzle that did not. What about these graphs? Do they have Hamiltonian circuits? Take a minute, it's a fun puzzle. Go through and see if you can find some. This one I think is particularly fun. So for this particular one, if you are not interested in doing this by yourself, I'm going to ruin the puzzle hunt for you here. I can start here. I can go along all the outer edges. And then once I'm in, I need to make sure that I don't visit every vertex more than once. So I can traverse the star in this direction and end up at the vertex that I started with. The next question to ask is the exact same question that we were wondering about in the Eulerian world. What is the rule, or what are the conditions for a graph to have a Hamiltonian circuit? These problems seem to be very analogous to each other, and in the case of Eulerian circuits, we came up with necessary and sufficient conditions. However, in the case of Hamiltonian circuits, it's not as simple. There are a lot of sufficient conditions that have been proven, but none that are necessary. So what we have here are lots of sufficient conditions, of which I will give you the 2 classical ones, but not anything that is necessary. So first up, we have what's called Dirac's theorem, named after the mathematician Dirac. A simple connected graph with more than 3 vertices, or at least 3 vertices, is Hamiltonian if degree of every vertex in the graph is at least half of the total degree. So here, n stands for the number of vertices in the entire graph. So what that means is, if I give you a graph, let's start with something very simple that we can actually check very quickly. What you need to do is compute the total number of vertices. So in this case, n is equal to 4, and compute the degree of every single vertex. In this case, the degree of every vertex is 2. 2 is, in fact, greater or equal than half of the total number of vertices. So Dirac's theorem guarantees that this graph will be Hamiltonian. Okay, and of course it's easy to check. This is a very simple graph. If you go all the way around, here's a Hamiltonian circuit. Now the problem though is the condition, if it fails, doesn't guarantee that the graph won't have a Hamiltonian circuit. So let's come up with a graph that's a little bit more complicated than this one, but has a similar structure. So let's say I actually start with a square, and then I'm going to have another square around it in this way. And then I'm going to connect the vertices to each other in this manner. So it's kind of similar to my original puzzle of the dodecahedron squished together. This is kind of like you took a cube, okay, where these are not visible, and squished it together from the front, okay? So plopped the front face onto the back one. So in this graph, what I have is that the number of vertices is 8, and the degree of each single vertex is 3, right? This is degree 3, this is degree 3. The graph is completely symmetrical, or what we call regular. The degree of every vertex is 3 for all the vertices. And notice that, of course, 3 is not greater or equal than 4, so Dirac's condition fails. However, this graph is actually Hamiltonian, and that can also be easily seen by just creating a Hamiltonian cycle. So let's say I walk all the way around the outer face, then I go in, walk all the way along this face, and back out. Here's my Hamiltonian cycle. So sufficient condition means that it is sufficient to satisfy this to guarantee a Hamiltonian circuit. However, it's not necessary. And there are many of these types of conditions. For example, another classical one is called Orr's theorem, and it has similar flavor, but now splits across different vertices. So here it says if the degree of one vertex plus degree of another vertex is greater or equal than n, for every pair of non-adjacent vertices, then G is guaranteed to be Hamiltonian. So let's take the same two graphs and see if this theorem is going to be strong enough to rule this graph out as having a Hamiltonian cycle. So once again, here I have n equals 4, and what I have to check is pairs of non-adjacent vertices. So for example, this one and this one. The degree of this is 2, the degree of this is 2, 2 plus 2 is 4, which is greater or equal than 4, so that holds, but I have to check every pair of non-adjacent vertices. So this is going to be quite the task, right? So I check these two vertices, and I again end up with 2 plus 2 is 4, which is greater or equal than 4. So this is a small graph. I only had to check two things. The Orr's condition holds, and the graph is guaranteed to be Hamiltonian. If I check this on this particular graph, so let's pick some non-adjacent vertices. For example, this one and this one. What I have is the degree 3 plus the degree 3 is equal to 6. 6, of course, is less than 8, which is the total number of vertices. So the Orr's condition in this case does not hold. Orr's condition, which is this condition for the degrees, fails. But once again, because this condition is only sufficient and not necessary, a failure doesn't guarantee non-Hamiltonicity. The failure just means that we can't apply this theorem and we have to look for something else. And people have been looking for something else for a very long time without actually being able to find it. In fact, Hamiltonian circuits are still an NP-complete problem, if that means anything to you. This is still a problem that is a big open problem in mathematics, as opposed to the Euler's that has been solved a long time ago. For this particular example here, I encourage you to go through and make some graphs to further familiarize yourself with the simple terminology and the structures of these graphs. So, for example, come up with examples of graphs that are Eulerian but not Hamiltonian. Examples that are Hamiltonian but not Eulerian, if that's even possible. What about both Eulerian and Hamiltonian? What about both but not the same cycle? We will now switch to talk about something that seems completely irrelevant, and then we will show what the connections are between the so-called gray codes and what we've previously talked about, Euler and Hamiltonian paths. So for gray codes, we're going to start by thinking about a switching network. Back in the early days of the course, we talked about those. You're thinking of n switches in this case, and the switches are going to be denoted by AI. So what you see is a sequence of switches where every single switch is a binary thing. It's either 1 or closed and allows the current to flow, or 0, open, and the current stops at that switch. So every possible state of the network can be denoted by a sequence of zeros and ones representing the state of each and single switch. So if we are thinking about a 3-switch network, a fairly small network, let's list all the possible states. This should be reminiscent of constructing a truth table for 3 different variables. So I can say I can start with 0, 0, 0, 0, 0, 1, or I can also think about this as counting in binary and increasing one at a time so that I make sure I don't miss any single numbers. And then of course, I know that if I have n possible switches, then the number of states for my network is going to be 2 to power n, right? I have n positions, and the counting principle suggests that because each one of them has 2 possibilities, 0 and 1, by multiplication principle, I get 2 times 2 times 2 n times, and therefore altogether 2 to power n. Well, it seems like we already know quite a bit about these networks, but here's a fun question to ponder. This listing was in the way that we count in binary numbers. Is it possible to list every n-bit word, so in this case 3-bit word, by changing exactly 1 bit at a time? So here, this ordering actually fails to have this condition, because look, when I went from this state to this state, I switched the 3rd bit from 1 to 0, and I switched the 2nd bit from 0 to 1. So this ordering does not satisfy this condition. But can I come up with one that does? Well, let's see. I encourage you to pause and actually try this for yourself. I can start with 0, 0, 0. And then I can have 0, 0, 1. It almost doesn't matter where I start. It sort of matters how I continue. So at this point, again, I can only switch 1 bit at a time. So let me switch the 2nd one, which will lead me to 0, 1, 1. And now let me switch the 3rd one back to 0 again. And now maybe I'll switch the first one, 1, 1, 0. Now I'll switch the last one, 1, 1, 1. I'll switch the middle one, 1, 0, 1. And now I'll switch the last one again to 1, 0, 0. I know that altogether I should have 8 of them, and there are 8 of them. And I can see that they're all distinct, so I've covered everything. And this sequence has another fun property, that it's actually cyclical, because the last and the first state or the word are also only differ by 1 bit. So this is something that I can take all the way around, and in fact, I can imagine these states as being around a circuit. This is what is called a gray code, gray after a mathematician Gray. It's a sequence of 2 to power n binary numbers where each consecutive numbers differ by exactly 1 bit. Okay? And if it closes, so if this property holds from the last to the first number, it's going to be called a cyclical gray code. That's a general definition of a gray code. Another type of gray code that we're going to be looking at are called binary reflected gray codes. And they are defined by the following recursion. So what I have here is I'm going to start with the gray code of 1-bit words, so 0 and 1. And then I'm going to construct my gray codes in the following manner. I'm going to take the previous gray code and append a 0 to the front of it. And then I'm going to follow up by reversing the previous gray code and appending 1 to the front of it. To get a better handle on what these look like, let's actually construct examples of gray codes up to length 3. So first I'm going to start with my G1, which is 0, 1. And because I'm going to be reversing it, let me write down the reversed one right away so I don't have to think about what it is. The reversed one literally means this code, but read in the opposite direction. So 1, 0. Excellent. So how can I construct G2? So this says I take the previous code, which is 0, 1, and I append 0 to the front of it. Okay, so I've taken this, and now I have to put 0 in the front. So 0, and then my first element here, which is 0, and then 0, 1. Okay, so this is my previous code, 0, 1, with the 0 appended to it. And then I'm going to follow up by taking the reverse of the previous, which I wrote down here, and appending 1 to the front. So I'm going to have 1s appear before each of these elements. So I'm going to have 1, 1, and 1, 0. And by inspection, I can see that this is indeed a gray code. Every time I move along, I switch only one bit at a time. Okay, let's see. How can we do that for the gray code of n-bit words where n is 3? Well, once again, I'm going to take the previous code, which is G2, and append 0 to the front of each single element of it. Okay, so all of these are going to acquire zeros at the beginning. So 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0. And then I'm going to take this code in reverse order. So let me write it down so that I don't make an accidental mistake. So this in reverse order, I'm just going to read all the elements backwards. So 1, 0, 1, 1, 0, 1, 0, 0. Okay, I'm going to take this and prepend 1 to the front. So 1 and then the element of this code. So 1, 0, 1, and then the next element of this code, 1, 1, 1, 0, 1, 1, 0, 0. I can see, of course, that every time I double the previous gray code, which results in powers of 2. So that seems quite consistent with the fact that this will be a gray code. And by inspection, for what I have so far, it seems that these indeed end up being gray codes. But I've only written them up to 3. How can I guarantee that this recursive procedure will in fact always produce a gray code? We're going to need a proof of that fact. And here, we're going to use induction to prove it. So all of the bits that we have covered in the course so far are coming to play their roles here. So for the induction, we're going to need a basis case. My basis case is, of course, going to be the basis case of my recursion. So 0, 1. This is a binary reflected gray code. Is this a gray code? Remember that a gray code is a sequence of all the n-bit words. So in this case, 1-bit words, where every consecutive one differs from the previous one by 1 bit. Is this a gray code? Yes, it is a gray code. So my basis case is passed. Next, I have to state my inductive hypothesis. For my inductive hypothesis, I'm going to suppose that GK produced by the recursion is in fact a gray code. So every single element differs by 1 bit. And in fact, let me just introduce notation here to make it easier later on. So let's say my elements in this GK are G1, G2, all the way up to some GS. And now my inductive step. For the inductive step, remember that I have to prove, so need to show, let's write this down, that the next construction, so in this case GK plus 1, is also a gray code. Well, very well. What I have is an actual recursion. So in order for me to start thinking about GK plus 1, I'm going to apply the recursion. So how is GK plus 1 constructed? According to the recursion, I took the previous gray code, which is GK. I appended 0 to the front, and then I followed up by reversing GK and appending 1 to the front. Okay, and listing these elements in a sequence is what produces my next GK plus first gray code. Now, the structures of these are hard to see, so let's write them out in terms of our introduced variables. So what I have here is, first, I have taken the previous gray code, so G1 through GS, and appended 0 to the front. So 0 G1, 0 G2, and so on, up to 0 GS. And next up, I've reversed the order of these guys, and I've added 1 to the front. So 1, and then reading from the end, GS, 1 GS minus 1, all the way down to 1 G1. So now my task is to prove that this is a gray code, which means that I need to justify the fact that in every single step what I have here is the difference in 1 bit and 1 bit only. Well, let's see what I have here. Remembering that this is induction, we're going to leverage our inductive hypothesis. I also noticed that, for example, if I look at these elements, all of them have 0 in the front, and the rest are the parts that were the original gray code on k-bit words. So G1, G2, all the way up to GS differ in 1 bit exactly, and prepending them all by 0 does not change that property. So by inductive hypothesis, we can conclude that these differ by 1 bit. We can apply similar justification to this portion. What I have here is my original gray code GK, and so these parts will differ by 1 bit, and prepending everything with 1, of course, does not change that. So here too, by inductive hypothesis, I can guarantee that in this portion of my new construction, every consecutive element differs from the previous one by 1 bit. And that, of course, leaves me with only one thing to check, and that is the fact that when I glue them together in this boundary connection point, I still have the property that they differ by 1 bit and 1 bit exactly. And of course, this is easy to see because here I have GS and here I have GS. So these parts are equal, and the first bit goes from 0 to 1. So these two also differ by 1 bit, and therefore, in my entire sequence, I have elements following each other that differ from each other by 1 bit. I already mentioned that I know that if this is a gray code, then this has the right number of elements. And by doubling the construction, I know that I have covered all of the possible bits of length n. And therefore, what I have in my structure is a gray code. Now, if you are struggling with generally jumping from an example to the induction like this, take a look at how we constructed the codes here one more time. So if I highlight, for example, let's go from G2 to G3, right? My G2 elements here appeared in this order, prepended with 0. So I was guaranteed, by the virtue that G2 was a gray code, that G3 will also be a gray code, because these portions were differing by 1 bit, since G2 was a gray code, and appending 0 in the front did not ruin that property. Similarly, for the second portion here, reversing the code, of course, keeps the property of differing by 1 element. So these portions were still parts that corresponded to elements of G2 and therefore differed by 1 element, and putting 1 in the front kept that property. And the only thing I then had to check was the middle portion, where the part that was copied from G2 was the same, and the different element was the actually prepended one. Go through this induction. This is a really lovely application of a technique that we have seen before and will be useful in these kinds of arguments. Now you're probably wondering to yourself, we were talking about graphs, so what do gray codes have anything to do with that? And let's see if we can tie everything together with the notion of a hypercube. So there are a number of different definitions that you can come up with for a hypercube, and they're all essentially equivalent. So let's go through a couple of them. We're going to start with this one. I'm going to take a set of n-bit words, so all 2 to power n, all bit words. So the size of Sn here is 2 to power n. And I'm going to draw a graph where every vertex represents one of the n-bit words, and the edges are going to be connecting two vertices that differ in exactly 1 bit. So in the gray code type of fashion, okay? So that graph is what we're going to be calling an n-cube. So let's start with Q1 here. Q1 means that I have 1 bit words there are two 1-bit words, 0 and 1, and I'm going to put an edge between the vertices if the corresponding words differ in exactly 1 bit. Well, here there is only 1 bit and they differ in 1 bit, so I'm going to connect the two. Next up, I have Q2, which means that I have 2-bit words. So what do I have? I have 0, 0, 0, 1, 1, 0, 1, 1. And each one of them corresponds to a vertex, and I'm going to connect the two if they differ in 1 bit. So for example, I have an edge here because those two differ in 1 bit. I have an edge here because those differ in 1 bit, an edge here, and an edge here. I will not have an edge here because 0, 0 and 1, 1 differ from each other in 2 bits. And similarly, I will not have an edge here. So you're getting the idea of why they're called cubes, because this structure is, of course, a square. So if I draw the third one, I'm going to have to think about how to properly situate my vertices so the structures may be clear. But as I already mentioned, I noticed that this is a gray code type of property. So if we look back on the previous page where I've come up with the way to list vertices in an order where they differ in 1, maybe this is somehow going to be inspirational for the drawing of Q3 that makes sense. I know that I at least have to have all of these vertices, and then it just matters about how do I place them on my graph. So let's say I'm going to start with 4 vertices in the fashion of the binary reflected gray code that all begin with 0. So 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1. And I'm going to connect them in the way that I connected the previous hypercube. And then I'm going to have vertices on the outside that all begin with 1. So I'm going to have 1, 0, 0, 1, 0, 1, 1, 1, 1, and 1, 1, 0. And if you look through, you will notice that I have used them all. Now I just have to connect the ones that differ in 1 bit. So I'm connecting these two, I'm going to connect these two, I'm going to connect these and these, as well as I noticed that I have to connect these two and everything along the diagonal. Now, of course, if I just asked you to construct this by yourself, you probably wouldn't have come up with the prettiest picture the first time around. And this is not my first time drawing a hypercube, so I knew where I was going. So don't despair if you were trying this out for yourself and you did not come up with the most visually pleasing representation of the hypercube. But this looks like something we've already seen. This is the graph that I have actually used as an example for why the sufficient conditions for Hamiltonian circuits are not necessary. And we can notice that the Hamiltonian cycle in this graph that we have traversed before in this fashion will correspond to something that we have seen just very recently. But before we do that, let's come up with the recursive definition of the hypercube. Noticing that what I'm doing is actually building every time upon the structure previously created. Here I went from an edge to 2 edges connected to each other, and then I went from a square to 2 squares somehow connected to each other. And I have a feeling that if I were to construct Q4, I would go from this cube, so I would draw, this is a cube if I sort of stretch it out, and then I will connect the corresponding vertices between these 2 cubes, creating the hypercube of the next size up. And that is exactly what we're actually doing for the recursive definition of a hypercube. We're going to start with a single edge with 2 points. So nothing special here, 0 and 1. And for the next one, I'm going to produce 2 copies of the previous hypercube. And in fact, I'm even going to label them as such. In the first copy, I'm going to prepend indices with 0. So let's say my top copy is my first copy. And in the second copy, I'm going to prepend indices with 1. And then I'm going to connect identical nodes. So connecting identical nodes from the first copy results in this graph. And now I'm beginning to really see these prepending structures as, again, very gray code motivated. So let's try it again on this copy. Okay, so what I'm going to do is I'm going to, well, actually, let me just redraw it. So I'm going to, for Q3, take a copy of Q2. So 0, 0, 0, 1, 1, 0, 1, 1. I'm going to take another copy of Q2. I'm going to draw it differently this time just to show a slightly different visual representation. Okay, so exact same thing. I'm just taking copies. In the first copy, I'm going to prepend everything with 0. And in the second copy, I'm going to prepend everything with 1. Okay, and then I'm going to connect. You can connect first, it doesn't really matter. I'm going to connect the identical nodes from each copy. So the nodes that were the exact same labels in the previous graph are going to get connected. So these two, these two, these two, and these two. Okay, and this is now my hypercube Q3. And again, it's actually the exact same structure. You can just think about squishing it from the front. So if I pushed this face all the way back and it ended up getting implanted in the center here, I will end up with a graph that looks like this. The next question is, well, if everything here is kind of gray code motivated, and on the previous slide, I came up with a way to list everything in order by the change of one bit, does this graph have a Hamiltonian path? Okay, so let's copy over this representation of it because it's a little bit easier to work with in the sense of graph theory. Okay, and does this have a Hamiltonian path? Well, let's start with 0, 0, 0. I'm going to go to 0, 0, to 1, 0, 0, and then 1, 1, 0, and then here, and then there, and all the way around the middle, and here we go. So yes, it has a Hamiltonian path. And the Hamiltonian path in this graph with labels has a special property that along this path, I am taking edges that exist. And edges in this graph exist if the two endpoints only differ in one bit. So by the virtue of constructing a Hamiltonian path in this graph, I have also constructed a gray code. Isn't that amazing? These labels, these sequences of numbers with the very special properties, somehow are connected to a Hamiltonian path. I think this is a little bit mind-blowing. And I remember seeing this for the first time when I was an undergrad, and this completely persuaded me that discrete math is something that I want to pursue for my research. Now, because these hypercubes have a recursive structure, you can also see how you can extend this reasoning to a hypercube on n-bit words. Here, I'm traversing the inside one and then using edges to go to the outside one. So if I have this and the next structure that looks exactly like this as well and has corresponding edges, let me just draw this super quick. So the next hypercube, Q5, is going to be this with the corresponding edges connected. So lots of edges in the middle, but I can see that in order for me to come up with a Hamiltonian path, I'm going to somehow traverse the inside copy of each one, use some edges to flip to the other one, and then use edges to come back. In the same way that I've sort of traversed the outside square here, went along the diagonal cube, traversed the inside square that is actually just Q2 embedded in it, and went back out. The recursive definition and this very strong connection to between Hamiltonian paths and the gray codes allows us to make that kind of leap, to justify to ourselves that a hypercube of any dimension will have a Hamiltonian path. And remember that I already mentioned that finding Hamiltonian paths is generally a very difficult problem. So finding graphs where Hamiltonian paths exist for any dimension is a big deal. And just as you thought that this lecture cannot possibly have any more random things thrown into it, let's talk about the problem of the towers of Hanoi that we have seen early on in the course. So recall that the problem is I have 3 different poles, and one of them has rings stacked from the biggest to the smallest, and I have to move all of them to a different pole. Generally, we move from the first to the last. You can only move one disk at a time, and you can only put the smaller disk on top of a larger one. So what we're going to do here is come up with the way to code this problem as a sequence of zeros and ones. So I am going to do an example with 3 different disks, and because my lengths of lines is difficult to keep constant, I'm going to have that the largest disk is straight, the second one is squiggly, and the third one is dotty. And what I'm going to do is code them in with the binary digits D0, D1, and D2 in the following way. Every time I move a disk, the digit that currently corresponds to it gets flipped. So everything starts with 0, 0, 0. And the moment I move a disk, for example, D2, whatever digit corresponds to it will get flipped to the opposite one. Okay, so because you've already seen the solution, I encourage you to pause the video, draw out the solution, and write out the strings that correspond to each single step of the solution. Okay, so what do we have here? My first step, your solution might be slightly different than mine, but the first step is going to be the same. I'm going to move the smallest disk over to a different position, let's say to the far right. That means that the bit that corresponds to the smallest disk will get flipped. So I'll have 0, 0, 1. Next, I am going to, there we go. Next, I'm going to move the second smallest disk over without touching anything else. So that means the bit that corresponds to the middle disk, D1, is going to get flipped. So it was 0, it's going to become 1. Next up, I'm going to move the smallest over to the middle disk. So my middle disk will now have the smallest on top here. And it's the smallest disk that got moved. So it's the bit that corresponds to D2 that's going to get flipped. Finally, I can move my largest disk over because everything else has moved off of the top of it and freed up an empty spot. So now I can have my other 2 disks in the same spot, but my biggest one is now taking up the space where it's going to rest, and its bit gets flipped for the first time. Excellent. Now, once I have that, what am I going to do? I'm going to move the littlest guy over to the empty spot. So that means that the bit that corresponds to the littlest disk gets flipped. Then I'm going to move the second largest onto the largest into its resting position. So second largest got moved, which means its bit got shifted. And in my final move, I'm going to move the littlest guy on top of the rest of the tower. And that is going to be my last step. It's the littlest guy that moves. So it's going to be its bit that gets flipped. And here we have the entire solution to the Towers of Hanoi problem and the corresponding encoding of our solution in a particular way with 0, 1 strings. Now let's take a look at the sequence of 0, 1 strings that we have come up with as the solution to this problem. Is this reminiscent of anything we've seen already in this lecture? Not only are these differ by 1 bit at a time, they're also constructed in the exact same way as the binary reflected gray code. The solution to the Tower of Hanoi problem is a binary reflected gray code. You can see the substructure here if you just highlight the smaller parts of the code. Notice how these are the same but flipped, the way that we have come up with it during our recursion and the inductive proof. And first, they're all prepended by 0, and then they're all prepended by 1. Isn't this amazing? How these seemingly completely irrelevant structures to each other are actually describing the same types of structure that underlies completely different problems. This is the beauty and the strength of discrete math. You can have 2 completely different objects, and come up with ways to study them that actually show some common underlying properties. Let's think a little bit wider in the sense of how can we use this newly found property of the solution of the Tower of Hanoi problem to come up with an iterative solution for a bigger Tower of Hanoi problem. So if I do have a binary reflected gray code as the solution, can I somehow use it and its recursive structure to solve a larger instance of the Tower of Hanoi problem? I'm going to leave that to you to ponder. I would also like you to think about how can you explain that we are actually getting a gray code as the result of the movements of the disks of the Tower of Hanoi problem in this particular way that we chose to encode them? And can you prove that? And the last bit in this lecture that I want to point out is a very famous problem that is related to the Hamiltonian circuits problem. It is, in fact, basically the Hamiltonian circuits problem, but with additional complication. The traveling salesman problem consists of a list of cities and a bunch of connecting routes that all have corresponding distances assigned to them. The question isn't just to come up with Hamiltonian circuits that visit every city exactly once. The question is to come up with the shortest possible route. This is an open problem that has actually been open for a while, and we do not know an efficient algorithm for solving it. So this is yet another very interesting aspect of discrete math. There are many problems in discrete math that are really easy to describe, even to somebody in a middle or even elementary school, but are still open problems. We still have no efficient solutions to them or no solutions at all. So maybe one such problem is just waiting for you.